everyone, welcome back to the class. I hope you have watched all of the previous sessions of this chapter, that is matter in our surroundings. And I hope you all get everything in those session also. So my dear students, what the thing is that this is the last session of this chapter. That means we have covered up all of the topics, and the topics which we are going to cover up today, these are the last topics for these chapter from the point of view of your examination, from the point of view of Olympiad as well, for your class ninth. Okay, I'm talking about not just for ninth because you are in ninth. Okay, so students, like in the last session, if you remember and if you have watched with the very great attention, so maybe you remember I have taught you some of the gas laws and what are the equations we are getting from it. Exactly, do you remember that? Okay, so students, today I have bring one of the trick for you so that it would be the easy thing for you, that how you can remember those laws. That ma'am, it will, you'll say ma'am that it is becoming difficult for us to remember all of these laws, all of the conditions, all of the equations. So what you can do here, it is the C. Okay, just let me check my trick because I have made this on my mind. So it is like G, B, A, and it would be P, V, T, N. So yes, student, if you remember for the Charles law, in the Charles law, what we did for the C stands for the Charles. Oh, I am writing down Char. So it's like Charles. Okay, let it be colorful. Don't worry. G for Gale-Lussac law. A for Avogadro law. B is for Boyle's law. So if you remember, student, we have kept something at constant in all of these laws. So in the Charles law, if you remember that what's the Charles law says that, or the Boyle's law says that. So the Boyle's law says that the temperature will be constant and the PV is equals to each other. Exactly, that the P and V are inversely proportional to each other. So that in the Charles law, pressure is constant, in the Gale-Lussac law, V is constant, in the Boyle's law, temperature is constant, and in the Avogadro's number of molecules are constant. How we, I have told you one thing also, that if we are having different gases in same volume, so we can also say that all of the gases are having the same number of molecules at constant temperature and pressure. Exactly, so that is the Avogadro's law. So these are the laws which we have studied till now. Now students, these are the topics which we are going to cover today, and these are also very important. Oh sorry, important. These are important, but as well as these are very easy also. Like you can see here that the Gale-Lussac law, Boyle's law, so these laws are here, and now we are going to study new laws today. That is the Graham's law of diffusion, Dalton's law of partial pressure, combined gas law, and ideal gas equation. And see student, all of these laws are only and only applicable for the gases. Okay, it's not like that for liquid and solid. Depending upon the property of the gases, we are getting all of these properties, because the effect of the temperature and pressure will be more seen in the case of the gases. Yes, solid and liquid also have that effect, but in the case of the gases it would be easy to see, because gases particles are very, you can know na, that the gases is very what I can say, gases particles are very having negligible force of attraction. We don't have to do so much of efforts for seeing the temperature and pressure effect. It will be very easy to see the temperature pressure effect. So that's why student, all of these are the laws which just generally, not generally, which just only talks about the gas law. Okay, so now starting with the today's session. Oh, I forgot to ask you, how are you all? You'll say, ma'am is just teaching us and she doesn't want to ask us that how we are. Okay, so yeah, we are going to discuss Graham's law of diffusion. So my dear students, do you remember what's the diffusion process is? So the diffusion is the process, student, in which the gases diffuse with each other, or the smell diffuse with each other, and we get one another type of atmosphere from that. So that is the Graham's law of diffusion. Now student, if I ask you who gave this law of diffusion, so exactly Graham has given this law, and that is why the law name as the Graham's law of diffusion. Now what this law says, that student, according to the Graham's law, at constant pressure and temperature, it says that the molecules or the atoms with lower molecular mass will effuse faster than the high molecular mass molecular atoms. Effuse means hota hai students, like if I tell you what is effuse, effuse means you can say it would be the escaping of an atom or a molecule through a hole. Hole means not hall, hole. You know that it happens with me. Hole. Okay. See, student, if you know this thing, students, like this LPG cylinder which we are using in our houses, it is connected with one pipe through with our stove, gas stoves. Exactly. See, student, what happened sometime by mistake? It happened that if the gas pipe is having any of the holes, so what we can see that there is the smell of the LPG in all of the surrounding. Why? Because gas has been effused out from that hole. So that is the effusion, student. When from any hole the atoms or the molecules of the gases escape out or release out, we call it as the effusion process. Exactly. And why we, and due to that effusion, we get that the LPG molecules or the particles of the gases has been dissolved, or you can say that diffused in the atmosphere, and that is the diffusion process. So we are saying this is the Graham's law of diffusion says that when we put the temperature and pressure, both of them at constant, these two are at the constant. So what will happen? The gas which is having the less molecule, that means you can say less molecular mass, will effused out more faster as compared to the gas which is having the high molecular mass. As in this picture, you can see that in this case you are getting that more of the molecules are coming out from the holes, whereas in the large particles we can see that they can't get out very easily. So student, if I talk about hydrogen and oxygen gases, okay, just look at it here, you will be getting the clarity about it. So if I talk about hydrogen and if I talk about oxygen, see student, hydrogen is having the molecular mass of 1 gram. You can write it down for the H2, it would be 2. If I talk about oxygen, so it is 8. Oh sorry, if I talk about oxygen, it is the 8, oh sorry, molecular mass we are talking about 16, and O2 comes out to be 32. So you can see that the molecular mass of the hydrogen is 2 and the molecular mass of the oxygen is 32. So which is having the more molecular mass? Exactly, it is O2 which is having the more molecular mass. So that's why student, the oxygen gas will effuse out slower as compared to the hydrogen gas, because its molecular mass is less. And if the molecular mass is less, student, so you can imagine, if see, if I ask you, if I'm having a basketball, okay, and if I'm having a cricket ball, so you can imagine that both are having different sizes. So basket, so the cricket ball, and if I'm having one hole, so what will happen? Cricket ball will be able to move out through that ball because it is having small size, and the big size basketball will not able to move out easily through that hole. So that's the point of view, student. When we have a small size molecule or less molecular mass molecule, so it will effuse out faster as compared to the molecule which is having the larger size or large molecular mass. So that is the Graham's law of diffusion. Fine, student. And this law says that, oh, just a second, students, I hope I haven't done anything wrong. Yeah, good. So they say, see, for example, student, if I say that the rate of diffusion, I'm writing it as R. Okay, I'm taking it as R, and the molecular mass, I'm taking it as M. So if I talk about hydrogen, so the R will be RH2 and the M will be MH2. So according to this law, the rate of it will be that if the molecular mass is less, so the rate will be high. So it is inversely proportional to the mass. So you can say that R is inversely proportional to mass, and it's the under root of it. Okay, so it would be MH2. Now if I talk about oxygen, so what it would be, that RO2 MO2. So it would be RO2 inversely proportional to the mass of O2. And if I compare these two, students, so what I am getting from here, I am getting this thing, that the RH2 divided by RO2 is equals to under root of MO2 divided by MH2. So this is the condition, student, for the Graham's diffusion law, because when you solve it, it will go upside, it will go here, and it will go here. So that's how we are getting this type of formula. And see, student, when the rate of diffusion, you can see when the mass increases, rate of diffusion decreases, and when the decreases, so the rate of diffusion increases. So that's the point of view behind the Graham's law of diffusion. Fine, I hope you are getting this point. Okay, so this is the Graham's law of diffusion. As I told you, hydrogen and oxygen, and the example of the basketball and the cricket ball. Basketball will not be able to move out through that hole, whereas the cricket ball will be like easily movable through that hole because of their size difference. And when the size is differing, so you can say the mass is also decreasing. Mass is also differing from each other. So the which is having the large molecular mass, it will having the high size, and that is why the rate of diffusion is less for it. So that's the Graham diffusion law. Fine, students? Good. Okay, now it's Dalton's law of partial pressure. Now you'll say, ma'am, what's the partial pressure? See, student, partial pressure, you can say that if one container is there, and in that container I am taking different type of gases, that nitrogen, oxygen, and hydrogen, three of these gases are there. So the pressure exerted by particular gas, that means if the pressure exerted by the oxygen, so I'll say that it is the partial pressure of the oxygen which it is exerting. So that is called as the partial pressure. So you can say that it is the pressure which is exerted by the individual gas. So the Dalton's law of partial pressure says that Dalton's law of partial pressure is a gas law which states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressure exerted by the each individual gas in the mixture. For example, student, you can also see in this A is exerting 4, B is also exerting the pressure of 4 atmosphere. Pressure is calculated into atmosphere. Okay, it's the unit of pressure. So when both are mixed together, so they will exerting the sum of it. So okay, so you can see from here that what's the Dalton's law of partial pressure. So it's like Dalton's law of partial pressure. So according to this law, students, if I draw one diagram here, okay, so this is the nitrogen, 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 nitrogen. Okay, and it's like oxygen, 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 oxygen. And which color should I take for hydrogen? uh, I'll take green. Okay, hydrogen, 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 hydrogen. So student, these there are having three gases, and which are these? So one is the nitrogen, one is the oxygen, and another one is the hydrogen. So student, the total pressure, the student, that the gases are always moving, so they will exert the pressure over the walls of the container because they all are moving, so they will collide with each other, as well as over the not that much collision, but whereas they will collide with the surface of the container. So that is why student, there is the development of the pressure. So you can say that the total pressure, the mixture of these gases which are exerting here, it is equals to the partial pressure of oxygen plus partial pressure of hydrogen plus partial pressure of nitrogen. So that's the point of view about the Dalton's law of partial pressure. So exactly, student, if I'm filling these three gases in one of the container, so if the oxygen is exerting 20, hydrogen 10, nitrogen 20, so the total will come out to be 50. So you can say that the total pressure which is exerting by the mixture of the gases over the container, it is 50 atmosphere. So that's the law, student, that the total pressure is equals to the sum of the pressure of all of these. Okay, so that's the Dalton's law of partial pressure. These all are very simple. I hope you all are getting this. Now combined gas law says, the combined gas law is a law which contains Charles law, Gay-Lussac's law, and Boyle's law. That this is the combination of these three laws. See, in the Boyle's law, what we see that the temperature is constant and we get PV. In the Charles law, it is V by T, and in the Gay-Lussac's law, it is P by T. So from this, what we have find out, one combined law. Combined law, how, student? See, it's like PV is equals to constant, P by T, V by T is equals to constant, and P by T is equals to constant. So after removing all of these constant and after solving this expression, what I have seen that it comes out to be PV by T is equals to constant. Okay, so this is the combined law. When we combine the three laws, that is the Boyle's law, Charles law and the Gauss-Lewis law, we get this combination, that is PV by T is equals to K. So I can write down it as in this form: the initial condition where that when the reaction or something has been started, so it would be P1 V1 by T1, which is equals to K, and the final we can write it down it as P2 V2 by T2, which is equals to K. Now both are same, so you can write down it as is equals to P2 V2 by T2. Even though student, in the previous session I was planning to tell you this, but then I thought that when the condition of the combined log came, so I'll explain you. So that's how we combine these three laws, and from this we get one equation, and that's how we can use this formula in solving the numericals as well. Fine. I hope you all are getting these points. So these are the three laws which we have discussed right now: Graham's law of diffusion, Dalton's law of partial pressure, and the combined law. Now we are left with only one thing, that is the ideal gas equation. See student, ideal gas equation is the equation which is followed by ideal gas. And guess what? We don't have any ideal gas, because I hope you have heard that thing that nothing is perfect or anything is no, what's that, nothing is perfect, no, कुछ भी perfect नहीं होता है. So yeah, exactly. So nothing is perfect. Even though if some like the if I talk about whole, like the people living on this earth, I can't say that any one of can be perfect in everything. It's like that some will be, it's like everyone is having their weak point. So that is why student, the same with the gases also, because we can't say that any gas can be ideal. So first of all, you should know what is the ideal gas. So the ideal gas, student, is that type of gas which is following each and every law, like each and every law of gas. For example, Graham's law of diffusion, that Boyle's law and everything. But student, it is not possible for any gas to follow each and every law at one particular time. It is not possible for it, that the volume is decreasing, so the temperature is affecting, or the pressure is not affecting. It's not possible. So that is why there is no such gas in the, like if I tell you in the surroundings, that we can consider it as the ideal gas. So what's the ideal gas, student? First of all, the ideal gas, we can say that which can follow each and every law, the law which we are studying from the starting, Charles law, Boyle's law, and these all laws. So we can't say that any gas is there or not. So ideal gas equation is the equation defining the states of the hypothetical gases. Hypothetical means we just can imagine about it, they are not in such real time, we just can imagine about it. So it's just that the ideal gas equation defining the state of the hypothetical gases, expressed mathematically by the combination of, like we have just to get one of the equation and we call it as the ideal gas equation. Okay, just give me a minute. Okay, so look at this video. Actually, before starting this video, I thought maybe this time the video is also not going to run like it happened in the last session. Oh my god, it's very disturbing sometimes. Okay.
Gas. It's all around you. It's in space. It's on Mars. It's dissolved in your blood and in your soda. It's everywhere. And it's easy to forget that we're submerged in an ocean of gas, but it's there all the time. You can feel it if you wave your arms around. You can't look cool while you're feeling it, but you can feel it. It's there, those little molecules and atoms bumping around against your hands as you wave them around. Feel it? Are you doing this? I've got good news and bad news about gases. First, the good news: when they're behaving themselves, it is extremely easy to describe their behavior theoretically, experimentally, and mathematically. The bad news is they almost never behave themselves. The first mathematical description of the behavior of a gas was a link between pressure and volume. In a closed system like the inside of this balloon, when we decrease the volume of the balloon, the pressure inside goes up. If we could somehow expand the balloon, then the pressure inside the balloon would go down. If I keep pushing on it, the pressure inside might go so high that it'll break. I
So he is explaining exactly like which we have studied in the Boyle's law, obviously, that when the pressure increases, volume decreases. Okay.
I can't do it. It's a very strong balloon. The relationship here is a simple one. When you multiply the pressure and the volume together, you get a constant. As long as the temperature and the amount of gas stays the same, so does that constant. It's called Boyle's law, and it was a pretty big deal back in the 1600s. It's also temperatures. Well, it was more applying pressure to them. This balloon is inflated 145 liter kilopascal per Kelvin mole. Temperature is experienced by you and me as hot.
See, students, he is explaining all of these laws only. So what we can see that the ideal gas equation is this, that is the PV is equals to nRT, which we get from the all of these laws. Exactly what I have tell you, what I have told you right now, that the ideal gas is that type of gas which will follow each and every law which we have discussed it till now. So students, you can see that if that type of gas is not existing in the nature, but we use this equation for solving the numerical, students, and we have all having all of these symbols which we are having in our what which we are having in our tell me which we are having in our, you'll say, ma'am, how we can tell. Okay, it's fine. So that which we are having in our laws. So it just, students, like it is the PV is equals to nRT. So I'll just explain you about the gas. So it's like ideal gas equation. See, it's like PV by NT is equals to one constant, and in the case of the ideal gas equation, we get this from the, like, you know, na, that's the, we have described the combined law. In the combined law, it is the PV by T is equals to some constant. So the ideal gas equation is also that thing. Then the combination of all of these law is equals to constant. But in this case, the constant is R, and this R is called as the ideal gas constant. Okay, this we called as the ideal gas constant, and this R is having different value like 8.314. It is already fixed, you don't have to worry about it. 0.0821 and more are there, and it all depends upon the units which we are using. So it's like PV is equals to nRT is the gas ideal gas equation. P is for pressure. Pressure can be in any unit, like atmosphere, it can be mm of mg can be used. Okay, volume is in ml or L, or it could be centimeter cube as well. N number of moles will present in the moles only. Okay, R, depending upon the units of all of these term, we use the R unit. T must be in Kelvin. Okay, so T is always in Kelvin in this ideal gas equation. So this is the ideal gas equation, student, but it is just used for the calculative part, because we don't such have any ideal gases in our atmosphere, so we can't say that any of the gases is following each and every law particularly. So that is why, student, we don't have any ideal gas, but we have discovered one ideal gas equation, so that we can use this equation and use that equation in the numerical part. So this is the PV by PV is equals to nRT. Fine, students. And if I show you some question over here, because we have covered up all of the topics. So what is the ideal gas? Ideal gas does not exist in reality. As I told you, it is hypothetical gas proposed to simplify the calculation. In ideal gas, the gas molecules move freely in all the direction, and the collision between them is considered to be perfectly elastic. That means the collision is perfect, which implies no loss in kinetic energy due to the collision. That means you can say, student, when any of the things collide with each other, so there is the loss in the kinetic energy. Exactly. If you know this thing from your physics chapter. So that is why, student, ideal gas, or you can say, like what I have told you, that the ideal gas are those gases which can follow all of these laws, gas laws, but we don't have any such ideal gas. Or you can say that the ideal gas are those type of gas in which the molecules are freely moving and all of the collisions are perfect collision. Because, students, whenever any reaction has to take place, there should be perfect collision between the molecules. If the perfect collision is not there, product can't be formed. Okay, so that is why, student, if the gases are having the perfect collision and everything is good for it, so we call it as the ideal gas, but it is the hypothetical situation. We don't have any such gases. Okay, now determine the volume of a gas. VI 3 liter, TI, I represents the initial. That means initially we are having this, and then F represent the final. That means after some time we are having this. So TI is given TF is given, PI is given, and PF is given. Now what you have to find out, you have to find out the VF, that is the final volume. See, PI is given, VI is given, TI is given, PF is given. And always remember student, if one of the unit is there, like for pressure it is kilopascal, so it should be the another one should also be in kilopascal. If there is the difference, so you have to convert it, and you can check that what could be the conversion factors. Okay, all are having different conversion factor. For example, 1 liter is equals to 1000 ml. If volume if one is in liter, so another one should be in liter. That means unit should match with each other. There should be no such difference in the unit. If the units are different, you will not get your correct answer. According to given parameters, we can use this equation, that is PV by, that is P1 V1 by T1 is equals to P2 V2 by T2, that is the combined log S. So substituting all of this, we are getting the final volume is 1.75 liter. So that's how student you can use all of these equations, all of these formulas by for solving the questions. Okay, so that's how, but it's just that you have to remember that the I represent the initial, that means starting. Final means, F means final, that means after some time the pressure is this, the volume is this, the temperature is this. So that's the laws and which we have to cover in this chapter. So my dear students, we have completed this chapter, that is the matter in our surrounding, with the point of view of your examination. And even though the Olympiad thing also, like all of these laws which we have to cover up, and I hope you get each and everything. And even though if you face any problem, any query, any question, you can post that question over the forum, on public and private forum of Ask IITians, as you know, and you'll get your answers. Fine students, so now this chapter has been completed. Try to solve question over it, try to use these formulas, and do better in your exams for this chapter. Learn this chapter carefully, because it is a very important chapter which you are going to have in your higher classes also. Okay, and it's a simple chapter, it's just about solid, liquid and gases. Okay, thank you students for this session, and yes, keep learning from Ask IITians. Thank you very much.